All right, welcome to the land of physics, just using a bunch of words and pointing at things. A company is selling a type of spring which has the following claim: the elastic potential energy of the spring is capable of storing for a given compression distance, does not decrease even after it compresses, stretches hundreds of times. Wow, okay. So how would you test that? All right. State a basic physical principle or law the students could use to design an experiment to test the company's claim. I would say conservation energy, right? If you're talking about elasticity, you're talking about the elasticity stays the same, compressed it hundreds of times. I'm going to use energy, right? Using a principle or law stated in the part A1, determine the equation of elastic potential energy stored in the spring in terms of quantities that can be measured using things you find typical in high school laboratory. So what I'm going to do is I'm going to stick a brick on it. I'm going to push it down. I'm going to let go of it and watch the brick go flying through the air. So I would use something along the lines of, let me get a pen. Yeah, it works. I would say energy before equals energy after, using the U's because it makes me happy. If you use E's, I would be fine with that. Now I would say that's 1/2 kx squared, which would be the energy of the spring, is equal to mgh. Why am I using mgh? Because I'm talking about it launching up into the air. Right? Okay, that's it. That's all I would do for the first little bit. Now I get the second. So now we're down the rabbit hole, right? I've already chosen my experiment. So if you would like to send me your choices, I will look them over and see what I think about them. I don't have a problem with that at all. In fact, I was anticipating getting a few of those, and I haven't gotten any. But that said, here is the dealio. It says here, design an experiment procedure that the students would use to collect the data needed to test the companies. Assume the equipment usually found in a high school physics laboratory is available. In the table below, the quantities associated with the symbols would be measured in your experiment. The equipment used to measure them also list the equipment that would be used to measure each quantity. Do not need to fill every row right now. So list the quantities and associated symbols you would need to measure in your experiment to make this work. Okay, so I'm gonna need to measure mgh, right? M. A mass of brick, mass of brick. I'm gonna say I call it brick. My symbol is gonna be M, and I'm gonna use a digital, oh yeah, digital scale, because I'm lazy. I don't want to use one of those fancy scales. G, I don't need to measure, it's universal constant. H, though, I need to measure, that's height. And I'm going to measure H, and that is going to be a meter stick. Okay, I need nothing else I need to measure to prove this quantity is true. I'm going to do it lots of times, whatever else, but that'll probably come later in my laboratory experiment. All right, explain how students should analyze the data to determine whether the company's claim is true, i.e. whether energy stored from the spring at a given compression distance does not decrease after the spring is compressed and or several hundred times. So you would say something like, compress spring by pushing a brick placed on top of it down. Past equilibrium. Place meter stick in background. Note starting place of center of mass of brick and how high it gets. And how high it gets using meter stick in the background and a camera accuracy. Yeah. Now, I am writing this out. Really, if this was a regular AP test, you would have a camera here. You'd say camera, draw an arrow. You'd say spring compressed, and then meter stick in the background. Meter stick in the background, dash, 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 dash. And then after let go, camera, and your meter stick, right? So if they're letting you, if they ask you to describe a procedure, if you are using your camera to take pictures of things, I would absolutely take advantage and do the drawings. They're saying you don't have to do drawings. My guess is they're going to try to ask a question you don't need a drawing for, but if they do, feel free to do this. And then last thing you'd have to write down, do this 400 times. Maybe just every 10th time measure. Okay, so that's how you do it. That's how I would do it. I've got my experiment. It's beautiful. It works. Can't complain. All right, so the students investigate 2 springs that hang up from a ceiling. They're going to take spring A and they're going to put some masses on it, and each mass changes how long it gets. It gets stretched more stretchy the more mass they put on it. 100, it's only stretched. So it starts at 25. At 100, it looks like it's stretched about 20 centimeters. At 150, it's stretched more like 27, 28, whatever centimeters. So then it says they're going to put spring B on there. They want you to graph it on the same thing. It's the same initial length. So the same initial length means that it's going to start in the same place, which is 25. Then it says it stores more energy as you, it stores more energy to stretch it, right? So it's harder to, hold on, it stores more energy? It stores more energy than spring A given for the given displacement. So it has to have more energy. Okay, so the force is kx. Energy is 1/2 kx squared. So the length must be going up faster. So this has got to be a wimpier spring that goes up faster. Something maybe like this, right? Because I need x to grow, right? We know kx is going to stay, is dependent on the mass, right? And that's the bottom. So if it stretches more, it would store more energy. Yeah? Yeah. Dang, I said that backwards. Rewind. Okay, so here's the dealio. I read the wrong question. I got to read the question. Take a little more time. It says here, the students following this procedure has the same equilibrium length spring A, but stores more energy than spring A for a given displacement on the graph above. Sketch which line of best fit would fit for the data contained in spring. So if I'm pulling at the same distance, would it not be harder to pull? Right? So it would be harder to, a heavier mass would displace it less to get the same amount of energy. Or another way to look at it is it's harder to pull because it's got to be a gnarlier spring because it stores more energy for pulling back the same distance. So the same mass is not going to pull it as hard. So actually it would be on the bottom. Let's hope I'm right. I mean, something like this. Okay, it has to start in the same place for the same reason I said before. All right. All right. So then the student's attaching 1 kilogram block to mass spring B, and then the student pulls the block down 1 centimeter, releases it. To measure the time interval for 1 oscillation. The students then repeat the procedure, but pull the block down 2 centimeters instead of 1 centimeter. What initial displacement of either is the delta T greater? Well, mass spring systems, delta T only depends on mass and spring constant, right? So period only depends on 2 pi square root of m over k, right? So how far I pull it, the amplitude doesn't matter to it. Amplitude does not matter. Pull it farther, it goes faster, right? Because it's being pulled harder. So delta T is the same in both cases, and that's my check. I think that actually finally finishes this monstrosity off. Sorry about that earlier problem with the